there's my function. In fact, let's talk about a couple things. Some of these are exponential growth, some are exponential decay. What is this one?
Would it be decay?
In other words, whenever this number is between 0 and 1, it's decay. Whenever it's 1 or greater, it's growth. I mean, even if I had y equal 0.999 to the x, that graph is going to decay, like something like that. It'll decay very slowly, but it will still get smaller and smaller the larger that x gets. Okay, if I replace the 0.999 with 1.01, then I'm looking at a graph that's going to get bigger and bigger and bigger as x gets bigger. Okay. Let's talk about domain and range. What's the domain of this function?
Domain equals the x value, right?
What's that? Yeah, domain is all of the allowable values for x. So what can we put in there for x? Is there any number we cannot put in there?
Can you not put in... I don't think there is any number you can put.
You can put in any number you want, from positive to negative. So the domain would be all reals. And there's lots of ways you can state that. Kind of like that's one of them. Another way, if I'm doing interval notation, is minus infinity to positive infinity. It's another way to state the domain. What about the range, which is all of the allowable values for y?
Would it be all real numbers as well?
Well, let's take a look at the graph. This is decay, right?
Yeah.
And we know that anything to the 0th power is 1. So this point right here has to be 0, 2. And it's just going to approach the x-axis the bigger that x gets. So now if we look at that graph, what are the allowable values for y?
Would it be anything greater than 0?
That's it. In other words, y is never negative here. Notice that when you have negative exponents, they do not mean negative numbers. It just means you take it to the other side of the fraction bar. So if I had 1/6 to the negative 2, that's the same as 6 squared. So it definitely does not mean negative numbers. Excuse me, I have to sneeze. And that's the thing that most people have the most difficulty remembering, is that negative exponents have nothing to do with negative numbers. In fact, as long as this is a positive number, this will always be a positive number, whether x is plus or minus. So our range is y greater than 0, and in fact there's no way to get y ever to be 0. The best way I can come closest to getting y equals 0 is to let x approach infinity. But even then, y just approaches the x-axis, which is the horizontal asymptote, but it never touches it. talk about this one. Domain. What's the domain? Best way to think about domain is to see if you can figure out anything that it can't be. It's more about what it can't be than what it can be. Because generally, unless you have an unusual function, x can be pretty much anything. Unless I said y equals 2 over x, now x can't be 0, but that's it. That's the only thing x cannot be, would be 0. Or if I said y equals square root of x, then x has to be greater than or equal to 0. Or if I said y equal log of x, x has to be greater than 0. It cannot even be equal to 0. So here's 3 cases where domain is restricted, but it's not hard to figure out the restriction. And that's generally the case. So the way to figure out domain problems is to look and see, is there anything that it can't be?
No.
So all reals. How about the range?
Wouldn't that be all real numbers as well?
Well, let's look at what this graph would look like. This is a translation of y equal 4 to the x. Okay? All exponential functions tend to look like that. In other words, you can't tell the difference between y equal 3 to the x and y equal 4 to the x, or y equal 10 to the x. For one thing, they all go through that point, which is 0, 1. Okay? So all exponential functions tend to look pretty similar. What 2 things do we have going on different from this or y equal 4 to the x? If I were to say this is y equal 4 to the x, how is our function different? Or how is it translated or shifted?
It's down 1.
Down 1, and what else? This means it's shifted 2 units to the right. Okay? So if I were to draw our function, I would first of all find this point right here and move it 2 units right and 1 unit down. And the 1 unit down ends up, instead of having a horizontal asymptote at y equals 0, we now have a horizontal asymptote at y equal -1, because I'm taking this curve and shifting it down. The fact that I have to shift it left or right, it doesn't really matter. It means I'm going to still have something like that. So this function looks like that. Now, what's the range?
Any number y is greater than -1?
Yes, exactly. Y is greater than -1. Now, there's a couple of ways of looking at this. You don't actually have to look at it graphically. There's another way of looking at it that I kind of like almost better. And that is, how small can that part be? If I was just talking y equal 4 to the x minus 2, how small would that number be able to get?
All the way in the negatives.
Well, it would look like this. So over here is where it's getting small. In other words, it can't quite get to 0, right?
Right.
Okay. Well, it can get big. Obviously, if x were 100, we would have 4 to the 98th power. And then subtracting 1 isn't going to make much difference. So it can go to infinity in that direction, but it can only get close to 0. Well, if this part of it can only get close to 0, then the range can only be at the smallest 0 minus 1. So therefore, y has to be greater than minus 1. Because this part of it is a vertical shift. So everything gets shifted down 1. And that never gets above minus 1. So when you have an exponential function like this, take the exponential part of it, this part here, and realize, well, I know this can never be negative. If x is hugely negative, like minus a billion, this would be awfully close to 0. So it can get very close to 0, and 0 minus 1 is minus 1. So it has to be greater than minus 1. What is the domain of this function? Domain?
All real numbers? Or
Can x be 0?
no?
Can x be negative?
No.
So what is our domain?
All numbers greater than 0?
That's it. And that's the only thing x can be. This actually is a more restrictive domain than this is. In other words, in my square root function, x can be 0. It can't be negative, but it can be 0 or positive. So this one would have a domain x is greater than or equal to 0. But the log function is even more restrictive. You can't even take the log of 0. What about this? What's the domain of that?
Would it be any number equal to or greater than 0?
Well, what our requirement is that whatever the argument is has to be greater than 0. So I can go from this and say x plus 6 has to be greater than 0, which means x actually has to be greater than minus 6. So that's the domain. In other words, take whatever's in the parentheses and set it greater than 0, and then just solve it. Okay? We didn't talk about range. Let's talk about range on that right there. This is what that graph looks like. You can see the domain x has to be greater than 0, right? It never goes to the left of the y-axis. What's the range?
The range, any number greater than 0?
Well, to find the range, look to the y-axis. What are the y values doing? What are the y values doing down here?
It's getting closer and closer to 0, but it's not touching.
But not the y values. The y values are getting larger and larger negative. So the y value actually can be negative infinity. In other words, this goes all the way down to negative infinity without touching the y-axis. And where does it go on the upside? Does that flatten out to a horizontal asymptote, or does it just keep getting bigger as x gets bigger?
It would just keep getting bigger as x gets bigger.
So your range is all reals. So on log functions, your range is all reals. On exponential function, your domain is all reals. And it's worth knowing that the log function is the inverse also of exponential functions. And one of the properties of inverse functions is they switch domain and range. In other words, if I told you y is equal to 2 to the x can be all reals, but y can only be positive. There's no way to make y negative. But if I gave you a log equivalent of this, it would be the log of y base 2 equals x. So that, now, I don't want to confuse you by talking about inverses and exponentials and logs, because when you take an exponential equation, there is the equivalent logarithmic equation. In other words, if I want to write that logarithmically, I know that logs are exponents. Base is 2, the argument is y. So that is the equivalent of that. But it also, there is another property of logs that you want to know about, and that is that logs also happen to be the inverse. Let's talk about this. I guess all of this stuff is fair game, given that you're going into pre-calc. If I put that function up, that's y equal e to the x. Okay? Now, I could give the equivalent logarithmic expression of that, but there's also the inverse of that. And notice what the inverse does. The inverse, in other words, this is y equal natural log of x. These two are not the same, but they are inverses of one another. And what does inverse mean? It means that graphically it is a reflection about the line y equal x. Always. All inverses are that. If you want to find an inverse function, draw a dotted line y equal x and reflect whatever this function is about that dotted line. And you'll have the inverse function. And that's true all the way through calculus. In other words, integration is the inverse of differentiation. You haven't had trig yet, but there's inverse functions with trig also. So most functions have inverse functions. And graphically speaking, they are always the reflection of that function about the line y equal x. All right. Let's go on. All I'm doing here is I'm drawing from the chapter test at the end of my exponential and log equation chapter. So the next question it asks is to simplify this expression. How do you multiply those two things together?
Multiply which things together?
These two functions.
You would set them equal to each other, wouldn't you?
No. If I had, let me give you an example. 4 to the 5th times 4 to the 6th. What would I do?
You would simplify the exponent and multiply them.
You would add the exponents. In other words, that's equal to 4 to the 11th. In other words, if I am multiplying same base, different exponent, I add the exponents. Okay? Well, up here, here's our same base. Now, we can certainly multiply 2 times 3. So the first step is to multiply 2 times 3, which is 6. But then when I go to multiply e to the minus 1 times e to the 2, what do I get?
Just e.
There's your answer. How about this one? Here I'm dividing. So what do I do with the, first of all, always do the number part first. So in other words, do that separate from the rest of it. What's minus 4 divided by 2?
-2.
E to the x divided by e to the 5x.
1 over 4x.
1 over e to the 4x, yeah. Now, I could just do it by subtracting the exponents, and I could write it like this, for starters. But in general, they don't want you to leave negative exponents there. They want you to turn it into a positive exponent, so that becomes this. Okay? What is this? Remember, e is just a number. A little bit like pi. Isa?
Yeah.
What's the result of that?
Would it be
Add all 3 exponents.
3 2x?
What is 6 plus x minus 3x? Six minus 2x. So the thing about exponents is that when you're multiplying same base, you just add all the exponents. If you're dividing same base, you subtract all the exponents. All right, let's simplify the following.
Isa, are you listening?
What's that equal to? Right, let's make it a little bit easier. Let's go ahead and put it's equal to some unknown value that we're trying to find. Okay. Now what? Can you solve for x?
Would you make it 2 log 1,000?
Well, that's a start. How would I rewrite that part of it? Write it exponentially. In other words, the one thing you definitely need to know how to do with logs is to go back and forth between the logarithmic expression and the exponential expression. Okay, what's the base? What's that base right there?
10.
Okay, and now what's the way I told you the way I remember it? Let's work with just that. Let's solve that. So how do I solve that? Remember, it's the number on the far left raised to the power of the number on the far right, or the variable.
Would it be 1,000 equals 10 times x?
10 to the x power. And part of the way I memorize it is I write it exactly the way I said. In other words, if that's my logarithmic expression, then I know that 10 to the x equals 1,000. Well, what's x? If 10 to the x equals 1,000, what is x?
100.
It's 3. Remember, this is an exponent. So,
yeah.
you see why it's 3?
Yeah.
Okay, because 10 times 10 times 10 equals 1,000. So by putting it in exponential format, we're able to solve for x very easily. Well, if x equals 3 here, I still have that 2. Let's not lose that. So this number is equal to 3. 2 times 3 is 6. Let me just do a few of these here. If 8 equals 2 cubed, give me the logarithmic expression of that.
It would be log 8.
When you say log 8, are you saying the base or the argument? The first thing you really should say is the base. So what's the base? Remember one thing. Logs are exponents. So what has to go over here?
That would have to be...
Logs are exponents. What is the exponent in that equation?
Exponent is 3.
Okay, so I know that much. Whatever the logarithmic expression is, I know that it has to equal 3. Now, where do the other two numbers go?
The base would be 2, and then the last part would be 8.
And the argument would be 8. Okay? So this is the way you write that. And then if I gave you that, and I said express that exponentially, then I'm going to take the number on the far right. I'm going to raise it to the power on the far right. Excuse me. I'm going to take the number on the far left. I'm going to raise it to the power of the far right, and it equals what's in the middle. So you need to be able to do this process. You need to be able to always go from this to that, or from that to that. That's the most fundamental skill you can have with logs, is to be able to go back and forth between the two. what is this equal to? In other words, this is the format b to the log base b of x. And that's always equal to x, no matter what b is. In other words, if I said 17 to the log base 17 of x, that's equal to x. In other words, if that is the same as that, then the result is just x. Or whatever that is. If it's x squared, then the result is x squared. In other words, if that were log base 17 of x squared, then that would be equal to x squared. What's this equal to?
That would equal x.
I didn't put anything in there because they frequently don't give you. They just say simplify this. Tell me what that's equal to. But we'll make it easier for you. I'll go ahead and add the variable. Now, to figure that out, put it in exponential expression. How would I put this in exponential expression, Isa?
You would do 1 equals...
Always start on the far left. Well, I mean, you have your way of memorizing and I have mine. You don't have to use mine. So go ahead. I won't interfere. What's the exponential expression of that? It's okay if you start with 1.
1 equals 17x.
17x like that?
Yeah.
No. 17 to the x power. There's a big difference. If I put the x down here, that is an algebraic expression. I can solve for x easily. X equals 1 over 17. But if I put the x up here, it only has one value for x. What is it?
Would it be 0?
Yes. X has to be equal to 0. Therefore, this is always 0. In other words, the log base anything of 1, I could have natural log of 1, that's also equal to 0. I could have log of 1, that's equal to 0. I could have log base 2 of 1, that's equal to 0. And the reason is because any number raised to the 0th power is equal to 1. So the one couple things you have to remember about logs is, first of all, the log of 1 is always equal to 0. In other words, I didn't really need that x. That's what it is. And the second thing is the thing I just wrote, which is the log base b of b to the x equals x. Isa, you still with me?
Yeah.
Okay. All right, let's solve the following. Let's solve some log equations. We have How do I solve that?
You add 7 to both sides.
Tremendous amount of background noise going on.
Yeah.
Okay. So now how do I solve that?
You add a log to each side.
Take the log of both sides. What kind of log?
Just a regular log.
Common log. In other words, the base 10 log. Which, if I don't write a base, that's what is presumed. Okay? So now, what is this side equal to? What is the log base 10 of 10 to the x plus 5 equal to?
Would it be x plus 5 log 10?
Just x plus 5. In other words, this is another case where if you have the log base b of b to the x, that's always whatever the exponent is. Notice why. Let's talk about that, because this is something you have to memorize, but you can always figure this out. Notice that if I wanted to, I can take this x and put it down here. So this thing is equal to the same thing as this, and that is always equal to 1, no matter what b is. In other words, if I had the log base 23 of 23, that's always equal to 1. Why? Because 23 to the 1 power is equal to 23. So whenever you have log base b of b to some exponent, it's just equal to the exponent. And the two ways to look at it is you can look at bringing the exponent down, and then I have x times 1. So that's why it's always equal to x. Okay, let's do another one. 5 minus natural log of x equals 7. How would I do that?
You would subtract both sides from 5.
Well, I think what you want to do is you want to get the numbers on one side and your natural log function all by itself on the other, right?
Mm-hmm.
So how do I get the natural log all by itself?
Wouldn't you just subtract both sides by 5 and then...
Well, let's do it in 2 steps. I don't want to leave you with the problem of having a negative sign in front of the natural log. So let's add natural log to both sides. And now let's subtract 7 from both sides. Because now what we have is 5 equals that. We're going to get rid of the 7. So now I have minus 2 equals natural log of x. So how do I solve that?
Would you just
do it whenever you're trying to simplify a logarithmic expression, put it into an exponential expression. And then you'll see what the answer is going to be. So put this in an exponential expression.
Would it be...
What's the base right there?
10.
No, what's the base? When it's natural log, what's that number? What's the base? E. Okay, so E to what?
E to the negative 2. equals
x. Exactly. And e to the negative 2 is just 1 over e squared. E is one of those numbers that's in your calculator.
wait 6. Okay.
All right. Let's do another one. How about what has to be true here? If the log base 2 of that quantity is equal to the log base 2 of this quantity, what can I say about the two quantities?
That you could get rid of them?
They're equal. In other words, this allows me to say that 4x equals x plus 15. And now it's a simple algebra problem. 3x equals 15, x equals 5. It's incorrect to think of this as dividing both sides by log base 2. That really is not what you're doing. This does not mean log base 2 times 4x. We don't even say that. We say log base 2 of 4x. Any more than if I say f of x, that does not mean f times x. That's just an expression, f of x. Same thing with logs. It's an expression. But the one thing I can do is exponentiate both sides to 2. Now, first of all, you see what I did there? It's important to understand what I did. Let me make it a little different. If I say x equals 3x minus 1, I can exponentiate both sides here. I can make that power of 2 and that power of 2. In other words, I can say, well, 2 to the x must equal 2 to the 3x minus 1. That's called exponentiating both sides, where you take the left side and you make it the exponent of whatever number you want, and you take the right side and you make it the exponent of whatever number you want. Okay? And so you can always do that, just like if I started out saying 2 is equal to that, well, you could assume that this has to be equal to that, because if 2 to one exponent equals 2 to another exponent, then the exponents can be equated. All right. Let's talk about inverses for a moment. If I say, find the inverse of that function, what do you do? How do you find inverses?
Would you multiply everything by -1?
No, there's a two-step process for finding the inverse, and it's really quite easy. Switch the variables and solve for y. That's all there is to it. Switch the variables and solve for y. Well, the first step, switch the variables. Now solve the second one for y. How do you solve that for y?
Add 1 to both sides and then divide by 2.
That's the inverse right there of that function. And I don't mean it's the same. It is not the same. But if I were to graph that, this would be the reflection about the line y equal x. That's what all inverses are. And the other thing about inverses is they undo what was done. If I said y equals the square root of x, the inverse is going to be y equal x squared, because this undoes that. That's the other key thing about inverses, is one undoes the other. Then again, these are not the same function. One is the inverse of the other. Well, when you're talking logs, in other words, if I say y equal log base 6 of x, tell me what the inverse is. What's the first step of finding the inverse?
You have to switch the variables.
And now solve for y. How do I solve that for y?
You would divide both sides by log base 6.
No, it's not dividing. It's exponentiating. And I wouldn't exponentiate both sides to log base 6. I would exponentiate both sides to the number 6. Okay? In other words, that's an exponential expression now. It's 6 to the x power equals 6 to the log base 6 of y. Well, why did I do that? Because that whole thing is equal to what?
That's equal to...
Remember, when this number is the same as that number, what is the whole thing equal to?
1.
Y. That's equal to y. So I've solved my problem. Y is equal to 6 to the x. That is the inverse function of that. And it doesn't matter how complicated it is, you want to do the same thing. You want to switch the variables and solve for y. The tough part about this problem is solving for y. In other words, this is what happened after we switched the variables. Well, solving for y is not the easiest thing. You have to somehow get that isolated, and the way you do it is to exponentiate both sides to the number 6. Because that, as long as this number is the same as this number, will always be equal to that. All right. Why don't we end it there, and I have a session with your brother. And I will call him back. Actually, I will just text him. Is he in the same place as you are, or is he at a different place?
He's going to do it in a different room.
Okay. I will text him the meeting ID number. I will close this one out and reopen it. All right?
All right.
All right, Isa, we'll talk to you next Friday.
All right.
Bye-bye.